Welcome to Chapter 15, Electrolytes, Acids, and Bases. You've probably heard of electrolytes before, especially when you drink things like Gatorade on a hot day or when playing sports, or even if you've been in a medical environment, you've heard the doctor say, let's order a set of electrolytes. So when we talk about electrolytes, especially in the medical laboratory, we're usually referring to any of these ions that you see listed here, but the most common ones are sodium, potassium, and chloride. Those ones we test for quite often in the medical laboratory, but it also includes things like calcium and magnesium. So electrolytes are a medical and chemical term for ionic salts. It's used in conducting electrical impulses within the body. We're going to talk about acids and bases as well, as those are a special subset. Let's start with an acid. An acid has some characteristic properties such as sour taste like a lemon. It turns litmus paper red. It eats away at active metals by reacting to produce hydrogen, and usually has a pH of 0 to 7. On the other side of the spectrum is a base. It usually tastes very bitter. It turns litmus paper blue. It produces aqueous solutions that feel slippery to the touch, and has a pH of 7 to 12. An example here is ammonia. And in case you were curious, a normal blood pH is 7.4. We use something called indicators to test for acids and bases. And there's different things that'll turn color. You heard me mention litmus paper in the last couple slides, but you can even use cabbage juice and some flowers. As you can see, there's red cabbage here, and adding it to different pH solutions will actually turn it different colors. Something that is neutral exhibits neither an acidic or a basic behavior. So modern acids and bases are based on the molecular definitions of the compounds. It's based on electrolytes and non-electrolytes. An electrolyte conducts an electric current, like you can see here, and a non-electrolyte does not conduct electricity. So does the solution complete the circuit? We've got a homemade and a store-bought example. If we put a gap in the circuit, we can see what happens here. Here are some common electrolytes and non-electrolytes. Some electrolytes that you're familiar with are probably acetic acid, such as vinegar, sodium bicarbonate, which is baking soda, sodium chloride, your table salt. On the non-electrolyte side, things like acetone, carbon dioxide, ethanol, methane, oxygen, sucrose. Those things are not going to conduct electricity. So when we talk about electrolytes, we talk about ions. Ions are the mobile charged particles in a solution. They carry currents in the electrolyte solutions. These are formed by the dissociation of ionic salts. I'm going to show you what that looks like in a minute, but let's look at this picture. Here we have an aqueous sodium chloride solution. Being positive, the sodium ions are attracted to the negative wire, and being negative, the chloride are attracted to the positive wire. Here's how dissociation works. Dissociation is the splitting of ionic compounds to individually charged components. It does not occur with molecular substances. So on the left-hand side here, you can see we're dissolving sodium chloride in water. So this is table salt. If you take salt and you add it to water, you stir it in, it dissolves into the separate different particles. Okay? On the right-hand side, we're dissolving ethanol in water, which puts intact molecules into the solution. They don't break apart. They maintain their molecular shape. So we have two different types of electrolytes. We've got strong electrolytes, which completely dissociate in water, and weak electrolytes, which only partially dissociate in water. In the bottom picture, you can see a strong electrolyte, which dissociated completely on the left, and a weak one, which slightly dissociates on the right. The weak electrolytes contain both the original compound and the dissociated ions. So of these solutions shown, which one contains a strong electrolyte, a weak electrolyte, and a non-electrolyte? Well, the left in the middle the left-hand side is strong, the middle is weak, and the end is a non-electrolyte. And we can look at strong and weak acids as well. A strong acid gives a large number of H3O ions when placed in water, and weak acids only partially dissociate it when placed in water. We can also have acid-base neutralization. This occurs when the H3O of an acid is counteracted by the hydroxide of a base. As you can see here, we've made water. So we have strong and weak bases as well. It's the same general definitions as acids. Strong bases readily dissociate to produce a high number of hydroxide ions, and weak bases only partially dissociate when placed in water. With acid-base neutralization, an acid and a base react to form water and a salt. Here we've got hydrochloric acid and sodium hydroxide forming water, chloride, and sodium. Be familiar with the definition of the Bronsted-Lowry acid definition. This is anything that donates a proton. The Bronsted-Lowry definition of a base is anything that accepts a proton. One thing we look at is pH. This is a special way to indicate how acidic or how basic a solution is. pH equals the negative log of H3O. This is sometimes called the Henderson-Hasselbalch equation that you'll learn about in clinical chemistry. But for example, if H3O equals 1 times 10 to the negative third, then the pH would be 3. Here's an example of our pH scale. This is the relationship between a pH and acidic and basic solutions. Anything less than 7 is considered acidic. pH of about 7 is neutral, that's about the pH of our body, and anything greater than a 7 is considered basic or alkaline. Here are some common substances that you may recognize and what their pH would be. Stomach acid is 1, okay, needs to break down food. Lemon juice is pretty low too. Go towards the middle, we see urine, saliva, milk, human blood around 7. And then we start getting up higher to the ammonias and the household bleaches and even oven cleaner, which would be considered lye. So that is all getting very alkaline. Sometimes we have a buffer, especially in the clinical chemistry department. We have reagents that we're using in the chemistry department to run reactions, and we want to make sure that the pH stays constant. So we add something called a buffer. A buffer is a solution that resists the change in pH. A solution that contains a conjugate pair of compounds refers to a buffer. It normally contains a weak acid or base. So as you can see here, we've got conjugate pairs, an acid and its base or a base and its conjugate acid. So here's an example of acetic acid and its conjugate base. Get acetic acid with acetate ion, carbonic acid with a bicarbonate ion, etc. The conjugate pair can then react with the addition of either an acid or a base. In this acetate buffer, the weak acid, acetic acid, goes after any hydroxide ions, and the weak base acetate ion goes after any H3O ions. So if we add OH, or strong base, to a sodium hydroxide solution, an acetic acid acetate buffer, the buffer replaces a strong base with a weak base at the expense of some buffering of the weak acid. And here, the buffer replaces the strong acid with a weak acid at the expense of some buffering weak base.